Thanks, Myron. Thanks, everybody. It's great to be here. So let's see. Um, Hi. Uh, I'm going to be talking about a quest I've been on for a while to reconstruct everything and the challenges that go along with that. I don't know. I hate to call it a journey, but I'll talk a little bit of my journey. I'm a big fan of architecture. I remember when I was a kid, I came across this great book called Cathedral by David Macaulay, who's a master illustrator, a master like explainer. He has this other book that's pretty famous called The Way Things Work, a kid's book that explains like how mechanisms work with really cool illustrations. But this book's all about, oh, I don't know, if you were living in 10th century France and you wanted to build a cathedral, how would you go about doing it? And it has all these great illustrations of all of the things you have to think about. So, okay, what tools do you need? What kind of craftsmen do you need to use those tools? How do you start? Well, I guess you dig a big hole in the ground and fill that hole with blocks. This like probably the foundation, actually several big holes, maybe for the buttresses. Um, and eventually you need to build a big wheel out of wood, and you use that to lift heavy stones up to the top of the cathedral. And so reading this, you get the sense that, not only is this cathedral aesthetically pleasing, it's beautiful, but it just, it's cohesive as a whole. Every part has a function. It just gels together, and there's a lot of thought that goes into it, and a lot of history that also goes into it. Another book along this vein that I really like is a book called The Story of Buildings, which is illustrated by this great illustrator called Stephen Biesti, who's a master at cutaway diagrams like this here. So the the illustration that really captured my attention is this one of the Notre Dame Cathedral in Paris, which is, it's a combination of like a cutaway diagram and an exploded view diagram. It's wonderful in so many ways. You see, the inside of the cathedral and the outside of this in the same image. You see, you see things like details of what's inside, you see inside the cathedral. You see like the substructures, like these beams here. You have all these captions that are explaining what the different pieces are. You have little people walking around, so you can get a sense of scale. It's just a very, I just love it. And you if you read these books and you see all these like very evocative words, everything has a name, like a flying buttress or a vault, or like even like more specific things like an archivolt or a tympanum. Just like this language of architecture, I found very, I don't know, just very beautiful and intriguing. And so I got really into the idea of architecture, and for all I've, it's been a quest of mine to reconstruct things, but um, computer vision can't quite reconstruct this. And I would really love it if we could reconstruct such rich models that are not just the surface of things, but also know about, oh, I don't know, what's inside things, what the function of things is, what materials are used to build things that are as rich as that illustration we just saw. And so, and it'd be great, I don't know, I personally think it'd be great if we could just reconstruct these beautiful, rich reconstructions automatically from data that's on the web, like Flickr photos, Wikipedia pages, and so on. Okay, so that's kind of my current quest, is how do we get reconstructions as beautiful as that one I just showed you? Now, what we can do in computer vision is kind of amazing in its own right. Yeah, as of about 10 years ago, we could reconstruct models like this with, tools like CoalMap. Here's a point cloud version of that Notre Dame Cathedral reconstructed from Flickr photos. And it's nice in its way. You have you have points, you have all these tourist photos. These are the camera locations that were reconstructed, where everybody stood and took their photo of the Notre Dame Cathedral. But it's a far cry from that Stephen Biesti illustration. It's, it's just this kind of point soup. It's missing all of the things that make that model very compelling, that make that illustration very compelling. But of course, these days we can go beyond these points. Here's like one of the latest methods in internet photo reconstruction. This is like Gaussian splatting applied to photos in the wild. So it's called wild Gaussians. And it's this very beautiful photorealistic reconstruction of the Trevi Fountain created from internet photos. It's, I've been working on this kind of thing for a while, and when I saw this kind of result, this blew my mind. But still, there's nothing, these are surfaces. I mean, literally, they're just Gaussian splat. It is a point soup floating in space. There's nothing behind this model. If you cut into it, it will be empty. it doesn't know that there's water here, and it can't make the water like move and flow in the right way. It's just like dead geometry in some sense. Okay, so these tools are getting pretty good. So like I said, for a while, it's been my goal to apply these tools like CoalMap and 3D reconstruction to everything in the world. So I don't know, starting maybe 15 years ago, I had this idea, okay, what if we ran CoalMap or the equivalent tools on all of Flickr? How much of the world could we reconstruct? Could we like cover the Earth in these point clouds and start to build up a model of the whole world? And so I had like, oh, we didn't have like GPU cluster at the time. I had a big CPU cluster just churning out geometry, downloading photos from the web, churning out geometry, and using geotags to place them on the Earth. And even then it seemed like, okay, maybe like these tools work pretty well. If we had enough images, we could reconstruct the whole world. So structured motion is solved, right? But is structured motion solved? I've come to the conclusion that it's not. And part of it is, if you go through the work of trying to reconstruct thousands and thousands of places, you quickly realize all the ways in which these tools fail. Okay, so I'm going to talk through some of the interesting kinds of failure modes and the ways we've tried to address them. So first of all, you run CoalMap or whatever 3D reconstruction tool on a lot of scenes, and you quickly realize that a big problem is symmetries and repeated patterns in the world. So here's a canonical example of this. This is St. Paul's Cathedral in London. If you download photos of it and reconstruct it with whatever tool, you probably will get a reconstruction like this. Okay, so this is a bird's eye view of a 3D point cloud, again, with reconstructed camera parameters. And I don't know, sometimes these are hard to interpret, but one thing you might notice immediately is that there's a dome-shaped set of points, and there's a dome-shaped set of cameras. Okay, I'm going to switch to laser pointer because it's going to be clear. Okay, you have a dome-shaped set of cameras, and you would expect them to be on top of each other, but they're not. One is far away from the other. And so the underlying problem here is that this scene has so many symmetries. Okay, this is a beautiful like Sir Christopher Wren cathedral, built to be beautiful and built to be like the model of symmetry. Everything, this dome has many symmetries. The building itself is symmetric. These clock towers look the same from 4 different sides. And so all of those SIFT matches or whatever feature matches that you get from these different parts of the building lead to a completely screwed up model. And that's not just true of the St. Paul's Cathedral. For whatever reason, London seems like the worst city for structural motion. Everything is symmetric, like Big Ben and the Tower of London, but lots and lots of buildings around the world are symmetric. This is a surprisingly common failure mode, getting models like this when you should get like an actual correct building. If you look closely, you'll see a whole bunch of problems with this, like surfaces colliding, things in completely the wrong place. And the underlying problem is something that I've been thinking about for a while, which is the idea of visual twins in the world, things that look the same at first glance, but are not the same surface. In fact, here's 2 images where almost no pixel is in correspondence between these 2 views, except for maybe some pixels inside the archway here. And if you run SIFT or even any modern local feature matching method, they'll very happily give you many, many high confidence matches between these 2 images. Like here's some examples with like a relatively recent method called light glue. So what I'm showing here are on the top pairs of images that shouldn't match. These are not overlapping surfaces. No pixel is in common between these views. And on the bottom, correctly matched images that should match. And you could say, okay, well, I'm going to just like run my feature matching and threshold by number of SIFT feature matches. And if it has enough, I keep it. And if it has too few, I drop it. But that totally doesn't work. You can very easily find pairs of images that shouldn't match, but have more matches than correctly matching pairs. It's kind of, I mean, it's pretty natural because when people are developing local feature matching methods, the primary consideration is I want to find all the matches that exist. You don't think so much about finding too many matches that don't exist. In other words, you're very happy to find positive evidence that things should match. No one really thinks about the negative evidence that things don't match. Like, okay, there's something in the background in one image, but not the other. So I think this is actually kind of a very interesting computer vision, almost like a philosophical computer vision question of telling the difference between things that look the same but aren't the same. I remember thinking about this when I saw there's this very interesting National Geographic article from 13 years ago on twins, and it had pictures of twins. And it made the point that, okay, you think of identical twins as being identical, but actually, if you stare at them closely enough, you'll notice subtle differences between them. Like, okay, maybe the nose is not the exact same shape, or maybe the pattern of freckles is slightly different, right? And so, you know, there's just, I think, this beautiful idea of trying to take two things that look the same and try and figure out that they're actually not the same. Like, what evidence do you look for? Even if people aren't identical twins, sometimes you might run across like a person who looks like another person. I think probably casting directors think about this. Like, I was watching the film Saturday Night, about the first Saturday Night Live episode on the plane, and they did a pretty good job of casting lookalikes to like Chevy Chase and all the like original SNL cast. Okay, so it's like, it's fun to find your own doppelganger, but in computer vision, this can be very damaging. Find doppelgangers in the world, or what we term doppelgangers, are kind of like evil twins. Things that look the same might completely screw up your structure motion algorithm, and that's bad. We don't like it. Okay, so just to show you, kind of illustrate a doppelganger pair, here's two images of opposite sides of the Arc de Triomphe in Paris. And of course, at first glance, they look exactly the same. You might confuse them very easily for the same thing, and there's lots of matches between these. But if you look closely enough, you'll notice things like, okay, these two sculptures don't match, and the buildings in the background, okay, they look kind of similar on this side, but maybe they're different on this side. The stuff behind here might be different. The markings on the road, you start to think about all the ways you can sort of pick out that these images aren't the same. It's like one of those like spot the difference games kind of thing. And this is, again, I find this problem very fascinating because there's a very interesting distinction between visual similarity and the physical identity of two scenes or two surfaces. So here's some examples of image pairs where on the one hand, you have two images on top here that pixel-wise look nothing alike. Like one image has lots of dark pixels, one has lots of bright pixels, but yet they are the same surface. They're both the front side of this Brandenburger Tor in Berlin. And then on the other hand, you have two images that look very similar from a pixel basis, but again have like almost no overlapping content. They're opposite sides of this gate. And so clearly we can't just rely on like any kind of like sense of visual similarity to help us with this problem. So what we did to address this in a kind of chain of work on this doppelganger problem is what you would always do in the modern era. You'd build a data set, and so, okay, how would you build a data set of what we want to find is lots of pairs of images that look the same but aren't the same, so that we use those as like negative pairs in a classifier to tell the difference between similar and the same. But building a data set like that is itself very hard because even humans can be fooled. There's this, okay, I've decided that I've discovered the hardest doppelganger, the world's hardest doppelganger scene, which is this statue of a cucumber in Ukraine, where I haven't yet invented a method that can distinguish between opposite sides of this cucumber sculpture. And so if you looked at this, you might say, okay, these are exactly the same. But if you look very carefully, you'll see, okay, this stem of the cucumber doesn't seem to match this stem here. So there must be some kind of difference between these sides. Anyway, the point is here, the human might very easily be fooled. So it's not like we can just like ask mechanical Turkers to label pairs of images as same or similar. So what we instead did is relied on the wisdom of the crowds in a different way. And there's a site that I really love called Wikimedia Commons, which I think is maybe criminally underused in the computer vision community because it's just such a wonderful resource of images, of millions and millions of images with very interesting categorization. And so in Wikimedia Commons, it kind of is this database of images undergirding Wikipedia and all the like wiki family of sites. But what it is a hierarchical categorization of imagery. So there's a category called cathedrals under Wikimedia Commons. And under that, there's subcategories of all the different countries and the cathedrals that exist in those countries, like all the cathedrals in Austria, all the cathedrals in Australia, and so on and so forth. And then somewhere under that, you'll find the Notre Dame Cathedral. But it doesn't end there. You can keep going and you can see, okay, there's a subcategory that's like historical photos of the Notre Dame Cathedral. There's a subcategory of, you can see some of them here, Notre Dame Cathedral and art. Love padlocks at the Notre Dame Cathedral. So some Wikipedia, editors have lovingly crafted this like tree of subcategories of all the interesting kinds of visual content in the Notre Dame Cathedral. There's not just one organ in the Notre Dame Cathedral. There's each organ in the Notre Dame Cathedral gets its own subcategory. And inside those subcategories, there's things like shamades of the great organ of the Notre Dame Cathedral. And if you don't know what a shamade is, you can go and find out that it's a horizontally pointing organ pipe. Whereas most organ pipes are pointing vertically. There's a special kind called a shamade that's pointing vertically or horizontally. Okay, so anyway, this is very, very cool, and just like you can get lost in a Wikipedia rabbit hole, you can get lost in a Wikimedia Commons rabbit hole. But the cool thing for building as doppelgangers is that people have also create subcategories by viewpoint. So you can find things like, I don't know, back left views of the Arc de Triomphe, back right views of the Arc de Triomphe. So you can find category labels that you can reason should not overlap, like the back right views should not overlap with the front right views, or so on and so forth. And then you can find images of those subcategories. And if they have matches, you can say, okay, here I've discovered some matches between images that shouldn't match, and therefore populate a data set of doppelgangers that way. And lots of scenes have these like viewpoint-based categorization. So that's very helpful for building a data set like this. So we built this original doppelgangers data set a couple of years ago, based on 224 scenes that had these kinds of viewpoint subcategories. And here's a few examples of doppelgangers, meaning images that don't overlap, but have lots of local matches. Arc de Triomphe, palaces, cathedrals, even a few cases that are a little bit different where Disney, I guess, maybe the Disney Corporation loves standardization. So each of the Sleeping Beauty castles in the different Disneylands around the world looks identical. And so you find matches between them despite, okay, here's one in Japan, here's one in either California or Florida, I'm not sure which. But they match each other despite being different buildings thousands of miles apart. Okay, so there's about 100, a couple 100,000 example pairs like this in the data set. And then you do your typical thing of, we have data, we can train a classifier. We have to be a little bit smarter about it. So what we do is we take an input pair. We want to classify it as a doppelganger or a true match. So we don't just feed in that image pair into some neural network. We first extract feature matches using SIFT or Lofter or some kind of matcher like that. And then we use those feature matches to align them. So you align with an affine transformation, and then basically the network can do a kind of spot the difference game. Now that the images are aligned, it can more easily try and scrutinize them to see, okay, can I find any detail that would clue me into these being different? So you feed in those aligned images and then the locations of the features and the matches, and then you feed that kind of stack of inputs into a network, and it classifies them as doppelganger or not doppelganger. And so this works pretty well. So we held out a test set, and if you train a doppelganger classifier on training set and apply it to a test set, so what you see is results like this. Okay, so let me explain. This is the average precision of the pairwise classifier. Feed in a pair of images, how accurate is it? It turns out that thresholding on the number of SIFT features seemingly isn't that bad. You get like 83% accuracy if you just threshold on the number of SIFT feature matches. Okay, but the problem here is that the nature of 3D reconstruction is that these matches will be fed into something like ColMap. Even a single incorrect match between a pair of images might make ColMap think that two surfaces are the same. So unfortunately, you have to have much higher precision when performing this task. So our method gets 95% precision, which is good. It's actually not, still probably not good enough, but it's good enough to get a noticeable improvement. And so, on a pairwise basis, here's some just interesting examples of correctly labeled doppelgangers and non-doppelgangers. So, here we have negative pairs. These are doppelgangers. These are images that shouldn't match. And our method correctly ascribes a low probability of them matching. Here's pairs of images that do match. These should be matching. And our method correctly ascribes a high probability of them matching, despite these image pairs, again, seemingly being much more visual dissimilar from each other, different seasons, different like times of day than this pair of images. So it's successfully learned to kind of discount these surface level similarities and look for the like more subtle cues that would lead you to believe that that leads you to conclude that they're not the same surface. Things like, things that don't quite match between them, or things like the background being different. Okay, so once you have this kind of pairwise classifier, you can then, use it in a COLMAP style pipeline where you first run the COLMAP feature detection and matching, and then you run this classifier to filter out all of the match pairs that shouldn't match, and then continue to run structure motion on the remaining successful the matches that pass that filter. Okay, so here's some results on applying this to the SFM problem. Here's a few kind of canonical doppelganger scenes. This is the Arc de Triomphe I've shown a few times. COLMAP has the problem that it only reconstructs half of the building because it glues the two sides together. That's a like common failure mode. Our method successfully disambiguates those two sides and reconstructs a complete 360 reconstruction. Here's another reconstruction that, on its face doesn't look necessarily wrong. Again, often these doppelganger issues are very subtle to where you can't even really maybe tell just from the point cloud that there's a problem, but there's indeed a problem. There's two copies of this tower, which it should be one. And also, should be a full 360 set of photos around it. And our method, again, successfully disambiguates this and glues the right things together. And just a more kind of top-down examples of COLMAP results and ARM results. And again, Big Ben is hard to see, but I think Big Ben is another really difficult case because of this four-way symmetry. And we get a successful reconstruction of that scene. Okay, so part of the reason for solving this problem is I got very annoyed that my automatic reconstruction tool failed so often. And so now that we've kind of patched this problem, maybe we can continue on this goal of trying to reconstruct all the world's scenes. Okay, so the modern version of this that we've embarked on is, okay, first you have to have a list of what are all the scenes in the world. We enumerated all of the scenes that Wikipedia knows about by using Wikimedia Commons. And we used it to create this data set called megascenes, which is a data set of over 100,000 SFM models from around the world, consisting of over 2 million open license images. That's the other nice thing about Wikimedia Commons, is that all the content comes with an open license because that's part of the terms of using Wikimedia Commons. This was created by, led by a couple students, Joseph Tung and Jean Cho. And we've also released all this data online with a permissive license, with also the hope of using this data to help train better 3D foundation models, I guess you could call them if you're into the term foundation models, like just methods that need lots of data. We're trying to provide that through this megascenes data set. But not only kind of the geometric data, but the other nice thing about Wikimedia Commons is that all the images come with rich metadata like captions and geolocations and the Wikipedia article corresponding to the site and so on. So, multimodality is a buzzword of today. People love multimodal data. And so this is imagery in context with a rich ecosystem of other kinds of data. Okay, so this harkens back to some other work from a few years ago where other folks used Wikimedia Commons to create a data set of landmarks for like location recognition kinds of tasks. This is a Google Landmarks data set. We set out to do something with the same data set, but to make it intrinsically 3D. So we, again, went to Wikimedia Commons. There's actually a couple other helpful members of the Wikimedia family that I think should be used again more in computer vision. There's a site called Wikidata that you can use to, it's a database, it's a much more structured database than Wikimedia Commons that you can do things like give me a list of all of the cathedrals in the world and point me to their Wikimedia page and their Wikimedia Commons page. Okay, so we found all of the Wikidata categories that seem to relate to buildings or other kinds of physical scenes. We use them to enumerate all of the instances of those scenes. Okay, like tourist attractions, some instances include the Acropolis, which is very famous, and some things that are maybe less famous, like the Antwerp Zoo. We want to reconstruct all of them. For each category, for each of those specific places, we go to Wikimedia Commons, download all the corresponding images as well as the all of the metadata, like what category they belong to, run 3D reconstruction along with doppelgangers and get 3D models. Okay, so 3D models with rich contextual information. Here's a few of them. These Wikimedia wiki scenes reconstructions. I don't know about you. I'm obsessed with reconstructing things. So this project really made me happy because I got to reconstruct, I don't know, maybe the most things that anyone ever has. I don't know if I can claim that, but the fact that it's so big really made me happy. To first approximation, it's though a reconstruction of religious buildings because that's the kind of, we just inherit what's common in Wikimedia Commons. It turns out that religious building is the most common kind of scene there. And to first approximation, it's like Western European buildings, but we do have coverage other places, including I was interested to discover some scenes in Antarctica. I think I can claim that every continent is represented in this data set. There's this interesting, if you do, again, like a Wikipedia rabbit hole, there's like a Wikipedia page of all the churches in Antarctica. I think there's 7 of them, which I wouldn't have guessed there's even one, but there's 7 apparently. And we have some of those reconstructed in this data set. And I encourage you to play with this. We have this all online. There's a web demo. Again, I really like playing with this. Okay, here's just like a visualization of that. You can start typing something, I don't know, like Tucson, and we'll autocomplete all the scenes that match that, and you can click on them and view the reconstruction. Here's just a few that I'll pull up. Again, I'm a real sucker for beautiful point clouds. This is a point cloud of Alhambra, I think, famous Islamic site. That it's beautiful. Actually, you get, I think a persistent problem in 3D construction though is like you run Colmap or whatever on a scene on a big set of photos, and you get, in general, lots of different separate connected components. So this is maybe the largest connected component, but you get a bunch of others too. I'd really love to be able to piece these together into a single coherent model. This looks like, this may be like a view of the outside, maybe like kind of a vantage point of I see like stuff that looks like trees here. Anyway, this is I don't know, I could go on and on. There's so many beautiful models. Here's like a fortress built into a mountainside. This is like Geonese fortress. You can see mountains and you can see structures, really beautiful point cloud. Some are not so big. I have to say, like, there's those really impressive big point clouds. And then there's a long tail of like things that only 3 people ever uploaded a photo of. So here's a Tucson landmark called Cathedral of St. Augustine. You can click on the image to see, okay, here's what it looks like. Not as impressive point cloud, but we have lots of them. And part of the point is this, to make a big diverse data set for learning, for any kind of 3D learning task. Good. Okay. Anyway, feel free, it's online, you can play with this. But, okay, we still were kind of disappointed because we still found that we got lots of doppelgangers even after running this doppelganger correction code. And even if we could correct it, sometimes we have to like tune the parameters because, again, you need very high precision. And so if you kind of are if you're too lenient about pruning doppelgangers, you'll get a wrong model. If you're too aggressive, your model will split up into a bunch of components because it threw out too many edges. So, it was still a big headache. And the doppelganger, okay, I mentioned that cucumber statue as a familiar case for doppelgangers. Um, uh, and the other thing is, because we've trained it on these landmark photo collections, we found that it didn't scale as well. It didn't work as well on kind of everyday photo collections, like your office buildings and so on. And so, we want really high precision, even higher precision than this original work gave. So that led to an improved version of this doppelgangers work called Doppelgangers++. That'll appear at CVPR 2025. And this was work done also under the RIVA program. And so there are basically two improvements that made a huge difference. One is that we got more and more diverse data, including more kind of everyday mundane scenes. And we, instead of using a CNN, we, I guess, upgraded to the modern world and built it on top of a transformer. In particular, we just took the pre-trained master, family of Duster master model and trained a classifier on top of that. And that worked much better. Okay, so in terms of data, this was in partnership with STR, and they partnered with a group called Vism, who builds a capture tool. And they captured data from sites around the world, not the landmark type sites, but again, things like residential scenes, office buildings, along with GPS and IMU data. And we use that metadata to help us distinguish between doppelgangers. And if two images are far apart and they match, that's a sign that they're a doppelganger. And using this Vism collection, we built a data set called Vism scenes of lots of doppelganger pairs. A more diverse set of doppelganger pairs. And then it turns out there's also lots of other online sources we can draw on, like Mapillary, which is like a kind of open source crowd-sourced street view that we gathered data from too. Okay, so we got lots of new data. We trained a better kind of backbone architecture, and here's some results. Okay, so I'm going to show you a few test scenes. So DG means doppelgangers. These are like your landmark photo collections. And I'm going to show you what happens if you use the previous doppelgangers that I talked about and our improved method. And I'm going to show you what happens if you train on doppelgangers images, or if you train on doppelgangers plus this new Vism scenes data set. Okay, so that's a lot to digest. But if your data is like landmarks, like your Notre Dame cathedrals of the world, everything works pretty well. But our new method works better because it's built on a better backbone. If you want to classify everyday scenes like office buildings, our old method doesn't work all that well. 0.8 is not particularly good. It's not going to help you very much. If you train on this better data, you get a big improvement. And if you train on a better backbone, I think almost maybe solve the problem. Okay, so I think this best classifier is, I would say, a very effective doppelgangers method. If you take a completely different set of scenes than you've trained on, Mapillary is not seen during training at all. You still get pretty good results with our best model. Our old model basically doesn't work at all. So I think we're getting much better at this doppelgangers problem. There's still ways to go, but we've made a lot of improvement. And you can see that in like actual reconstructions. So on the top row, these are what you get with a more recent than Colmap 3D reconstruction method called Master SFM. These are broken in all sorts of ways. Even things like kind of a nested doll of a model where a big part of the scene becomes a small part of the scene, nested inside some other, tucked inside some other geometry. I'll just suffice to say we do much better in practice reconstructing these difficult scenes. I'm going to start to accelerate slightly, but because I kind of want to get us back on time. So anyway, the code and data is available. It's all things you can run and integrates with Colmap. Okay, so there is one thing. Okay, so this is something I'm very excited about, which is, okay, another perennial problem that came up several times today is sparse imagery. How do you reconstruct a scene where you only have sparse views? Here's two images of a indoor scene. I think there's very little overlap. So, to give the answer, this is like a room with a U-shaped set of desks, and this image completes the U, the side of the U that's only partially visible in this image. Okay, and traditionally this is a very, very difficult 3D reconstruction problem. If you run a model like Duster, one of these newfangled methods, it doesn't do particularly well. It reconstructs these parts of the scene in completely the wrong place. Oh, well, maybe not completely, but it doesn't do a very good job. Why doesn't it do a good job? I'm not actually completely sure. Maybe it's because it hasn't trained on enough data, or maybe because it's under the hood using a regression kind of transformer method. Maybe it's hard at ambiguity where there can be multiple correct answers. Dave has worked on things like cameras as rays, where it's more diffusion based. Maybe it would do better. I don't know, but it's a hard problem. And so my student Rojan, working as a Google intern, there's maybe an obvious way you could try and solve this problem nowadays, which is, okay, can we use video generation models? I think maybe that's a very common idea these days. Like, can we use video diffusion models to solve our problem? Because video diffusion models, people are talking about this like this world model. And so you can use these video diffusion models where in the mode where you plug in a pair of images and ask them to interpolate. Okay, and if you plug in this pair of images and ask, I think, one of these recent methods like Dream Machine to interpolate, it does a good job of understanding their physical relationship. Okay, now why is it good at this? Well, I think there's an argument that the best video model might be better at 3D reasoning than the best 3D model like Duster, simply because it's very easy to train a video model on the most amount of data possible, like all videos in the world. So, and in order to train these models, you need some other annotations like 3D geometry. So I think, at least in the current world, it's probably the case that the best video model knows more about geometry than the best kind of specifically 3D model. And so if you then take this video and run that through Duster, you get a more correct reconstruction of this scene, where you kind of have this correct U-shape desk configuration. Okay, so this is the premise of a paper led by my student Rojan, and that will appear at CVPR during her internship at Google. And it's not that this works completely as a turn-crake thing. You still have to think about it, because at least the current generation of video generation models are very creative. So you give them two images, and sometimes it just makes up something that kind of looks like a video, but is not 3D consistent. So in this case, in these two cases, it's morphing at a certain point. It's trying to find some creative way to link these images, which is not, moving the camera in the correct way. At a certain point, you get a morph that turns the scene from one thing into another scene. Here's another example, the kind of failure mode of these generative models. They can create new objects. So here we're trying to pan from a sink to a microwave. And so it moves the camera in such a way that it can put a place for that microwave and make it appear. Okay. And here's another example of an inconsistent object shape. Like maybe it's watched the movie Transformers and it knows that, okay, I can kind of take an object and transform it into another one. And that's what it's doing here, instead of making the camera move in the right way. So you have to deal with the fact that these methods can be very creative. In fact, I guess they've learned more than just 3D consistency. They've learned other things that maybe could happen in the world. And so to make this work, we have to have some way to tell if or select videos that are consistent. So the idea is we're going to actually run these models many times. Like this is the world's most inefficient camera pose estimation method. You call a generative model several times, generate several videos, and hopefully some of those videos are correct, like this one, even if some of them are incorrect, like this one. Okay, it's like panning up to see this desk above a sink. Here's like a more correct interpretation of what the relationship should be. Okay, so you have to, the kind of boils down to, reduces to the problem of figuring out which video is good. And to do that, we have a simple idea of, we take a video, we extract frames from it, we take subsets of those frames and run Duster or master on each of those subsets. So we pick a subset at random, we generate a Duster reconstruction. We pick another subset at random, we generate another Duster reconstruction. And the idea is that a good video, all of these different reconstructions should be consistent with each other. And for a bad video, they'll often be inconsistent because objects appear in weird ways and in non-3D consistent ways. And so for a wrong video like this one, the predicted rotations and translations you get from running these multiple master runs will be inconsistent. Whereas for a correct video, they'll tend to be much more aligned. So this red point is like a single point where all the predictions are overlapping instead of these spread out purple points for a inconsistent video. Okay. We evaluated this on a few different data sets. And you can try different video generative models like Dynamic Crafter, Runway, Dream Machine. We tend to get improvement, and that improvement can range from fairly small. So we get a few percent improvement in rotation estimation for this kind of Cambridge scenes data set. For ScanNet, we get a much more noticeable improvement in things like the camera translation estimation. Okay, compared to just Duster as a baseline. Just to show you some qualitative results, I don't know, I find this very interesting and intriguing, and even wonder like, okay, what are the limits of this? So here's two images from, I guess, panning down looks like a typical London street kind of situation. Duster doesn't do a very good job, gets a high error. And our method somehow reasons that these images are, you could argue that there's probably multiple correct interpretations of what the scene is. It correctly reasons that these scenes are next to each other. I guess maybe that's part of the bias of being trained on video models, is that it expects maybe a pan is kind of a common way of getting between two scenes. Whether that's correct or not, at least on the test scenes we tried it worked pretty effectively. It also has these interesting, okay, so it has to somehow invent this person. So it invents a person walking into the scene. It's very interesting how these models work and how they can be used for 3D tasks. Okay, so if you take this generated video, you get a much lower reconstruction error and a much more plausible scene. Okay, I think I'm going to skip ahead. Here's another interesting one where our method gets a much more correct answer than Duster, even though there's some creativity in how it's like a scene where there's like toy animals positioned on the side of a planter, and it makes them like walk around in this weird way, even though in the end it kind of gets the right camera motion. So there's this interesting interplay between the nature of how these are trained and how they can be used for 3D reconstruction. And arguably this is good, because if the scene really were dynamic, you would want the model to explain kind of the dynamic motion of the things in the scene and tease that apart from the camera motion. So I think arguably this is a good sign. Okay, I think I'm a little over time, so I think I'm just going to show a couple more things and conclude. I want to kind of get us back on track. But I think a couple other interesting open problems are the fact that the world is 4D instead of 3D. That temporal aspect operates at a few different scales. There's a scale of years, over time the Notre Dame Cathedral changes, even though it's a static building, because of fires or restoration and so on. So every time we seek to do 3D reconstruction, we're kind of lying to ourselves. What we really should be thinking about is 4D reconstruction. Sorry, I am going to skip because I really want to keep us on time. But I want to say, just give a pitch for one project that I think is really cool, in the vein of dynamic 3D reconstruction, which is called MegaSAM. This is a recent SFM SLAM method led by Jungchi Lee that will appear at CVPR. That is a very fast and robust SLAM method, robust to videos of dynamic scenes. Okay, so here's a input video with like a moving camera. Sorry, why isn't this working? Let me try that again. Oh, why don't I just click on this link? That's going to be better. And these interactive examples are more fun anyway. So we have this nice like point cloud viewer where you can see, okay, here's a video of a dog, it's moving. The camera's moving too. It's kind of correctly reconstructed a dynamic point cloud and correctly reconstructed the camera motion. There's a bunch of examples. If we have bad internet, I think this is going to just be a fool's errand to click on these. So I'm just going to go back to the presentation. So just to conclude, I think 3D reconstruction is actually a very exciting area. We've made a huge amount of progress, but there's still a lot of challenges. Okay, here's my wish list of 3D reconstruction. I want complete 3D models that are complete both inside and outside. I don't want these separate models of the inside and the outside. I want everything to be kind of puzzle pieced together in the right way. Reconstruction from sparse imagery. There's a lot of progress, but I think still a lot of open questions. I want to transcend the Colmap paradigm. I want to transcend the idea of we feed photos to Colmap and we get back geometry. I want to feed photos, but also like Wikipedia articles or videos with audio. I want a multimodal Colmap that can take in all sorts of information and that like talks to LLMs. It should know that like in the 10th century, they built scenes out of this material and use that to inform how we do 3D reconstruction. Okay. I want computer graphics ready models that are interactive. So like if I have a scene of the Trevi Fountain, like I want the water to splash. I want to be able to touch things and have them be interactive in the right way. I want fully semantically aware 3D reconstructions. I want to be able to point at something in a model and have it tell me what it is. Sorry, my Zoom is restarting, I think. And I also think generative 3D models is a big open area. So with that, I thank you for your attention and thanks to all the people, the great people who worked on these projects. Thank you. I lost my Zoom. I don't know if we have time for questions. Yeah.